Hi there guys, well welcome back. We're about to do 5C, and 5C is a bit of a hodgepodge here of ideas. We're talking about bias, we're talking about reliability, we're talking about measures of central tendency, we're talking about measures of dispersion, and histograms as well, but only histograms with equal size class widths. In other words, bar charts. Okay, so bar charts really. Okay, so there's lots of bits in here, and I suggest that as you go through, or as I go through this, you just write a few notes as well. So I'll try and make it, relatively quick. A little bit of discussion about these things, just sort of digest, unpack some of these issues. But I suggest that you come up with some little notes as we go through as well. Right. Well, there is here. Some hints on how to do this investigation, and they're doing an investigation into the mean length of a population of pencils. Fascinating. Okay, well, good. Okay, well, you're welcome to have a go at that. It's good to read through the hints here. I'm not going to do the investigation myself. There is a little box here at the top here, though, which is talking about what bias is. So most people generally have some sense of what bias is, but the definition they're giving it is that bias in a sample can be defined as concluding some incorrect statistical information. Okay, so we are manufacturing the sample in such a way that we're getting out a conclusion which is incorrect from the data. Okay, and this tends to give a skewed interpretation of the general population. Okay, so maybe we've chosen to sample, for example, we're trying to find out how much homework people do, and we're in a really great, hardworking mathematics group, and we ask everyone in our group how much homework they do, and we're going to use that to reflect how much homework people do in the general population in your year group. Well, that would be a biased situation, because the way in which we've constructed the sample is to only have taken from a really top group of students. So we'd have a skewed interpretation. So we would expect in that case that we'd be getting out people who put a lot of effort into their homework, perhaps more than in other groups, for example. Okay, so there's an example of bias. Now, in terms of skew, we just have a little look. So let's look at positive and negative skew. I was looking at this before everything crashed. And here we go. Let's look at this one here. And there we go. You can see positive and negative skew. We can see that positive skew. Okay, let's just take this thing here. Okay, so our positive skew here is a situation where everything is going slow. There we go. There we go. So positive skew is actually talking about a distribution where we're kind of more loaded to one side than the other. And when we talk about it in terms of frequency distributions, where here are your frequencies, we're talking about this being skewed towards the y-axis. So a negative skew would be saying, well, actually, we're skewed in the opposite direction. We're kind of loaded towards the other end of our domain of values which we're interested in. Now, a situation of no skew would look like the normal distribution. So we'd be saying, well, no, it's kind of a symmetrical distribution. There's no skew at all. So skew in terms of frequency graphs looks like this. Positive skew is actually towards the axis in the negative direction, if you like, loaded towards the start of your domain. When they're talking about skew, of course, they're saying it tends to give a skewed interpretation of the general population. When they're talking about skew, they're just saying we're getting out a result which is not consistent with the general population. So not necessarily what we're talking about there in terms of negative and positive skew. But I thought I'd just mention this because it's kind of interesting in terms of how to load up your frequencies within the domain. Okay. So let's shift on. We're talking about sources of bias next. So, it says here, it is essential that each sample is representative of the population and bias has been minimized or eliminated. So that's what we seek to do when we're choosing one of our sample methods. And remember, we had 5 sample methods, which we talked about in the last exercise. Now, here we've got 4 different sources of bias, which they're breaking it down into. So again, I would write some notes. Remember, what were your 5 sampling methods? And now, what are your 4 sources of bias? Well, 4 sources of bias, for example, you could have, we could have here, first one, it says, some members of the population being excluded from the sample frame. Okay, and they come up with the situation of saying, well, let's go through the telephone book, which was, an old-fashioned way of collecting a sample would be to call people up, and there used to be telephone books, believe it or not, which were delivered to every house, these massive books which gave you the telephone numbers of everyone and all businesses in a particular area. Well, now some people aren't necessarily registered to be on that list or have taken themselves off the list. So if you're just calling people, making a systematic sample from telephone book, then you're likely to miss people who don't have telephones. And back in the day, where maybe having a telephone, let's say in the 1950s, was a luxury item, you'd probably only be calling people who could afford that. So you'd have this kind of bias already built into your sample by only interviewing people who had the money to buy a telephone. For example, that's like your classic case of people being excluded from a sample frame. Okay. Now, non-response is another source of bias. So, for example, some people don't respond, and there might be a certain type of people who do respond. It might be that people who respond to a questionnaire which is being sent out are the type of people who like to complain, who are thinking, well, I was going to make a complaint anyway, but this is making it really easy for me. And maybe people who are content with maybe the service they're getting, for example, maybe they're just happy enough to let it continue as it is and don't want to reply. So, if you've got to think about the possibility that some people don't want to respond to your questionnaire, or some people identified for the sample aren't going to respond. Okay, right, so that's a possible issue of carrying out your survey, potentially in terms of a questionnaire. Okay, so there's also the possibility of getting biased through a bad design. So, for example, if your questionnaire is unclear, if it's ambiguous, if there are leading questions, then that's going to be part of a bad design. So a leading question would be, for example, to say, don't you think I should get a grade 7 for my maths? Or don't you think you should get a grade 7 for maths? And you say, well, yeah, I think I should get a grade 7. But don't you think that those questions which start off with sort of a leading question, which is saying, it's leading you down one way of thinking. It's kind of suggesting that really this is the right way to think. Don't you think that you should vote Labour in the next election? Is suggesting that actually Labour is the obvious choice. Why would you choose anything else? You'd have to be crazy to do that. So that would be a bad design. That would be a case of a leading question. But obviously your questions need to be clear. Obviously they need to be unambiguous. Obviously you shouldn't have tick boxes where you could tick onto either of 2 different cases and both would satisfy your thought of your answer. For example, you have, I don't know, how many hours of homework do you do a night? 0 to 1 or 1 to 2. Well, maybe I do 1. Maybe I fit into both. So okay, because that could be an example of bad design. And finally, we've got this bias by the respondent. So this is saying that You know, if you ask someone their age, their health, something about their health or their weight or their income, there's lots of things which people don't want to talk about, especially if, as they say here, the truth is negative. So yeah, you've got to think about, if you're asking personal questions, whether or not you're likely to get truthful answers. Okay, so that's the kind of bias that you can get when you're, especially when you're creating questionnaires as your means of surveying this sample from the population. Okay, and now they're talking about reliability of data. So we've got 4 points from bias, and now we've got 2 points about reliability as well, which we come up with underneath. But first of all, just let's define what reliable data is. Well, reliable data is so data from your sample. Okay, so not necessarily the data of the entire population. We're talking about the data that we're collecting from our sample. We can say that this is reliable if, when you repeat the data collection and then analyze that data and obtain results, then each time that you do that, the outcome to what you find out from this survey, from your results, is likely to give you a similar outcome or similar findings. But reliable data is not necessarily the same every time, but if we repeat this process, we're likely to get reliable data if the process gives us similar conclusions each time. And again, it says the data is sufficient as well. So definition for sufficient, if there's enough data to support your conclusions. Okay, well, again, this is not your normal kind of mathematics. There's a lot of definitions here before we actually get into analyzing the data. And, you know, it's worth just jotting down these points and coming up with some notes for yourself. Okay, so they're talking about representative things as well. So what is representative? They're saying when collecting data, you might ask, how many data items should I have? And of course, there's no fixed number, but you need to ensure that you collect enough data so that your results are repeatable. Okay, results being repeatable means that you then have sufficient data. And likewise, results being sufficient means that the data is reliable. Seem to be very similar things. Okay, but then it also says that that you collect enough data so that your results are repeatable and are representative. And representative is to say that they represent the whole population well. So it's not only that we want to get similar results, and not only have we got sufficient data to support our conclusions, but we're also actually representing the population well. Well, if the data is reliable and we've got sufficient data, then it should be representative, because you should be able to repeat the process and find that we're getting the same conclusions about our population. Okay, now perhaps if your data is reliable and you're repeating the process, you're getting similar findings which are not consistent with the population because of your an error in your sampling. But we do want to ensure that we are getting something which is representative of the population. Okay, right. I mean, these definitions are tricky, right? But these are likely to be a 1-mark reasoning question to come up with a couple of suggestions as to how to improve a survey, or how to eliminate bias, or how to come up with your sample, or why a sample is good, or why the data is reliable. The data is reliable because we can repeat our survey to obtain similar results. The data is sufficient because we have enough data which supports our conclusions. The data is representative because it represents the population as a whole. We're trying to represent the population as a whole. Okay, right, I'm going on a bit, sorry about that, but you know, we have a little bit more here. We also have this last little bit before we actually go into some mathematics, into some sort of actual mathematics with numbers. We're talking about unreliable data. Okay, well, unreliable data. So unreliable data could lead to bias, by the way. So we seem to be sort of overlapping here, but they're giving two reasons why there could be unreliable data. And firstly, well, let's put it around the other way around. There could be errors in the way in which you've handled your data. Maybe that you've put in numbers into your answers from your questionnaire in the wrong place. Maybe that comes from the survey being asked or the questionnaire being asked with issues in the way in which the questions are constructed, and people didn't know where to put things, but then data is ended up being put in the wrong places. Perhaps that's an issue, but maybe they're really talking here about saying just data might be entered incorrectly by the person putting it in, or just handling errors at some stage, or by the mathematician dealing with this. And columns in the table might get muddled up. That's a source of error. That's just a processing error by a human who is dealing with this situation at some stage through from sample all the way through to processing the data. Okay, and the other problem with your data is you could be missing data. You might have people who are not responding. There's a lack of response to questionnaires. Or maybe it's not possible to record the data. See what they're saying here. They're saying, for example, if you were surveying the number of cars on a road at different times of day, maybe it's not possible that you possible at night, as you would probably be asleep. Maybe that's an actual just constraint of being able to collect the information. Okay, so missing data reduce the validity of a sample. Again, it's creating a problem with our conclusions and can create bias. Okay, well, I'm going to stop there. Am I going to stop there? No, let's look at this point here because it's kind of interesting. It's saying you can actually minimize missing data by getting rid of those types of questions which say not available, not applicable, don't know kind of answers. Don't give people the option to say that. Another thing you can say as well is when you're giving questionnaires, when they say, how do you rate this? Is it bad? Is it good? Or is it kind of, okay? They often say get rid of the middle option, because at least, if you have 4 boxes, you're saying it's, very bad, it's bad, it's good, or it's very good. At least then you're getting a conclusion from someone to say, well, is it slightly bad or is it slightly good? You can't get people sitting right in the middle. So it's here it might be that everyone plumbs for the middle, whereas here we're likely to get an answer when we average these results out to either one side or the other. Okay, right. So I've said enough there. There's another little bit of inquiry skills there. We're now going to talk about descriptive statistics. So we're going to talk about measures of central tendency, and maybe you've not called them these before. But we're really talking about the mean, median, mode, and so the mean, median, mode, yeah. That's what we're talking about for measures of central tendency, somewhere around the middle of the data. And we can talk about them as just averages, but they talk about them here as measures of central tendency. Essentially averages, what we normally call averages. Okay, and the sort of the normal one which we talk about when we're saying, well, what's the average of, I don't know, the results in your group for the last test? Well, the average you'd work out by saying, well, I'm going to add them all up and divide by how many I've got. And that's just the mean average. And I'm guessing that you know the mode and the median average as well, but they're useful at different times as well. So median is just the middle of our data set. So it's ordering things and saying, well, look, here's our first place, here's our 5th place, and the middle person is going to represent the median. In other words, their result will represent the median. Okay, so that's kind of nice actually. The median is good because, if, say, for example, you're interested in finding out how much the average wage is in a company, and you find out that, on a scale for X, you've got lots of people who are not earning a great deal, you know, on that scale, and then you've got one CEO who's earning way more than everyone else, then this guy's an outlier. But the median would take just the middle of these values here, and it would seem we've got 6 here, so we'd have to average the middle two, or the salaries of the middle two employees, and that wouldn't be affected by the kind of extreme value for maybe the company owner or something like that. So you know, sometimes the median is good, right? And so anyway, it's saying this one here. Let's put my words together properly. This one is the mean, and here's the formula for the mean as well. So the mean of a sample we call x bar. And x bar is the sum of all of our x values divided by how many people we've got in this sample. Now they have a slightly different way of writing it here, and I'll talk about that in a moment. But we can use this dummy variable I is equal to 1, so first person, all the way up to our nth person here. Okay, now if that's going up to k, that should really be k on the bottom there, I think. So there we go, we're just adding together all of our values, adding together all of our scores, and dividing by how many people we've got. Now another way of doing this would actually be to say, okay, well, listen, I've got 6 people who scored 100%. So I just want to do 6 times by those 100%. And then I got 5 people who got 99%. So I want to do 5 times those 9 people who got 99%. So if you've got lots of values which are the same, maybe you have 100 people who've got a shoe size of 8. Okay, so you want to do 100 times by 8. You don't want to keep adding all those 8s together. So we can change the formula a little bit here, adjust it to say, well, we can do the sum of all of our fx's, where f1, for example, is the frequency which is associated with the outcome x1. Okay, so if we sum together all of our products here from I is equal to 1 all the way up to n, then we can divide by the number in our sample again as well. Now, also the number in the sample can be seen to be the sum of all of your frequencies, because you know, if you've got 10 people with a shoe size of 8 and 9 people with a shoe size of 7 and so on, well, if we just add the 8 and the 7 and so on, then we'll find all of the total number of people which we have as well. Now, this you probably know in a table format, and that's talking about, I don't know, let's look at goals scored. We could say number of goals scored in a match, 0, 1, 2, 3, 4, and we can say the frequency here. We could say, well, this has happened 5 times, 6 times, 2 times, 1 times, 0 times. And now if we times those things across, that's going to give us our frequencies times by the thing that we're interested in. So, sorry, the thing that we're interested in here. This would be our x in this case. Now, if you times those things across, you'll get no goals added here from these 5 matches, 6 goals added here, 4 goals added here, and so on. And if you add all of these up, you'll have the total number of goals. And that's this thing here. And if you add your frequencies up, that's this thing here. And then you do a division of the two. So you're probably used to doing this from a table. Right, again, I'm still going on. One more thing to note, though, that x bar is used for sample mean, but the population mean is normally written as mu. So that's said as mu. And normally we can use x bar as an estimate for mu. So if we can't work out the population mean, we use x bar as an estimate for mu. Okay, right. So there we go. So that's what they're saying there as well, actually. Now they're talking about the mode. So mode is just the most common value which occurs in a frequency, in a set of data, thing which occurs most frequently in a set of data. If there's more than one value, then you can say that the thing is bimodal. You know, so if there's more than one mode, then it's bimodal or trimodal, or it's just got multiple modes. Okay. Actually, that's not what they said there. The second point that they've made there, let's just pick this apart. Okay. They've actually said if there is one value that occurs most frequently, then that value is the mode, and the frequency is the modal value. Okay. They're saying that the modal value, that's interesting as a definition. The modal value is the frequency attributed to the mode. No, I've not defined things like that previously. Let's have a little look. So modal value, meaning the mode or modal value is the data value that appears the most often in a set of data. Yeah, in fact, the modal value is the same thing. So the book there is saying, I think that's kind of wrong. The book is saying the value is the mode value and the frequency is the modal value. No, it's not. Mode and the modal value are the same thing. Okay, and in a frequency table, this value is, or interval, sorry, in a frequency table, this is the value or interval taking the highest frequency. Yeah, okay. Maybe I've kind of misinterpreted this here, but I think that that's said wrong. But either way, anything that's said wrong in the book, this is an old copy of the PDF. I'm not using the online version, so just so I can scroll through. But there's just sometimes these little issues in the old version of the PDF, which has been ironed out in new versions of the book. Okay, median. Median is the value in the middle position. Okay, and importantly, that's the n+1/2th term, or the average of the n/2 and the n/2+1 terms. Now, it depends on whether you've got an odd amount of data or an even amount of data. So, if you have 5 pieces of data, you can do 5+1/2 gives you the third value here, which is the one in the middle. Okay, so one in the middle, we always need to do this trick of adding 1 and dividing by 2. If you have 100 pieces of data, then the middle piece of data is the 50th and the 51st. You have 50 on one side and you have 50 on the other side, and in the middle you have the 50th value, but the start of the next one is going to be the 51st value. And that's what they're talking about here. N divided by 2 and n divided by 2 plus 1 gives you the two terms which you need to average in order to find the middle term, if there is strictly no middle term. And that's going to happen when you have an even amount of data. Okay, well, we still go on here, and it's going to go on a little further, still a fair bit to discuss. And so there's measures of dispersion, and we have many measures of dispersion for statistics, but here we're just talking about the range. And the range is simply the highest value which you have in your sample, take away the minimum value which you have in your sample. Okay, so that's all it is. And obviously the range is not always that good if we've got an extreme case in our set of data, if we have an outlier or a rogue value, which will affect our range greatly. So what we often prefer to use is the interquartile range, which is saying, well, what's the range of the middle 50% of people? Or we've got the standard deviation, which we could use as well. And we'll talk about that later. Okay, so now we have quartiles as well. And so quartiles are talking about what's the lower quartile, what's a quarter of the way through our data, and what's 3/4 of the way through our data, which is going to be called our third quartile or our upper quartile. Now, a lot of people would have done this before, especially from drawing cumulative frequency graphs. But this is very similar to find. These values are very similar to find as the median. So the two quartiles are going to be quite easy to find by doing n+1/4, so a quarter of the way through the data, but with that adjustment of +1 on the numerator there. And likewise, for 3/4 of the way through the data, we're going to say 3/4 of n+1. That's where we're going to find our position. Now, the interquartile range is another measure of spread, and that's what I just mentioned a moment ago. It's talking about taking 3/4 of the way through your data, the value we're getting from that, and then subtracting the value which we're getting from 1/4 of the way through the data. Now, so there needs to be a little discussion of this, I think, because when they're talking about these formulas, they're saying, how do you get Q1? Well, you get it by doing n plus 1. So like this. N plus 1 divided by 4 through your data. Now, that's nice if you've got, say, for example, 11 values, 5, 6, 7, 8, 9, 10, 11. Because when you do 11 plus 1 divided by 4, you're going to find your third value. Changes into third, by the way. Okay, so when we've got 11 pieces of data, 1/4 of the way through is the third one, and 3/4 of the way through is the 9th piece of data. And the median turns out to be the 6th piece of data. So that's nice and easy. But what happens when you have 12 pieces of data? So you've got 6 and 6. Well, the median we already know is n divided by 2 and n divided by 2 plus 1 to get the measurements which we require. So they're the people we're going to choose to get the measurements which we need. So the median is already somewhere in here. That's the median. But if we want now the lower quartile, we'll have to take 12 plus 1 divided by 4, which turns out to be 3.25 through the data. Okay, now 3.25 is 1/4 of the way between these two values. So it's not like we can just say we add these two together and divide by 2, because actually we just need to go 1/4 of the distance from this value to this value. So that creates that issue. Now, to be honest, people don't worry too much because it's all a little bit imprecise. It's a bit of an art rather than an exact science at times. So to be honest, to find the median, what you would normally do is just go halfway between those two. That's fairly obvious, and that's described already. But in this case, what would you do? Well, you could go 1/4 of the way between the third and the fourth value, and that certainly wouldn't be wrong. But what most people do is say, well, listen, when we've found the median, let's split the other half into 2, and let's take the median there. And let's split this half into 2, and let's take the median there. Now, you won't be wrong in either of those cases. But, I mean, this is kind of more right to do the same essentially as what we would be doing for the median. Let's find 1/4 of the way between the third and the fourth value. So let's look at the difference between the two things. Let's find 1/4 of that difference and let's add it onto the third value. Okay, so another thing to mention is that if you've got 200 pieces of data, often people just say the median is at the 100th piece of data. And so when data becomes large, you've got 2,000 pieces of data, you take the 100th to find the median. Okay, and that's like in the case when you've got cumulative frequency graphs, you'll remember perhaps that, if this is your n, just generally go to n over 2 to find your median on that graph. If you don't know about these graphs, don't worry about it. But, if you've seen it before, you realize that this is the process we do to find the median. Okay, and we do that when, n is large. Now, that doesn't make the rule which we've got for the median wrong. It just means to say that sometimes this will be sufficient. It's a discussion point, really. Okay, right. So histograms. So histograms here, they're talking about just the ones where we've got essentially like bar charts, where you've got bars with equal widths. Now, with histograms, we're talking about, again, let's just get one up, okay? So we're talking about situations like this, so something like this. And we're basically putting on an x-axis here, which is an x scale. And then on each of the bars, you're leaving no gaps. With a bar chart, a lot of people think that you need to leave gaps, and that's up for debate, really. And if you don't leave gaps, and if you put on a proper X scale at the bottom, then you're actually coming up with a histogram. So for example, here they're talking about weights, and weights being between 9.5 and 20 there, I think. So they're really saying, well, how many weights are between 19.5 and 20? Well, you know, we're talking about continuous data here. So for continuous data, we need, you know, an x-axis with real numbers on, where x is defined to be, you know, your real numbers there. So you might also need to just create a category to say, well, where do we include 20? Do we include it in this one, or do we include it in the next one? And again, that's something to discuss. You know, so it may be that you include it in the first one and not in the next one. Okay, you can see in this case, they've included 20 in the next one. But to be honest, given that it's continuous data, you can always zoom in closer to get your value to decide whether or not that 20 is really 20.01 or if it's 19.98 or whatever it is. I guess because if you've actually collected data and you've done some rounding off, then your 20 would really be potentially rounded off from 19 point whatever you've rounded to. So maybe that's why you would include it from the previous one, because you would normally round up to 20 when you go from, say, 19.5 to the nearest whole number, you go to 20, whereas 19.49. I don't know. This is a discussion. It's really not needed. I'm really overthinking this. I'm sorry. I apologize. Okay, but sometimes you'll have equals on one side and sometimes you have equals on the other side. Okay, right. Okay, so there you go. I mean, they're giving you essentially. I mean, it's interesting, isn't it? They're giving you here steps for drawing an equal class size histogram by hand. They're telling you how to draw a bar chart. We've gone from doing implicit differentiation in the last section of the last chapter in cases where there's related rates of change in applied problems, really sophisticated mathematics, to this box here telling you how to draw a bar chart. Okay, you can read it through yourself, okay? So I think I'm gonna stop in this case. Okay, they're talking about class intervals. Class interval is the difference between your 18 and your 20, that's 2. Draw your frequency histogram. In order to do that, they've made a table first, and then they've drawn the graph. You can see that, and then they're doing the same in the next one, I think. Okay, I don't think there's anything difficult about those questions. Determine whether you should use a bar chart or a histogram. The data is discrete because we are counting, not measuring. Okay, so number of chicks hatched from 24 days. Yes, I'd say it's discrete, in fact, because you can't have half a chick, you know, so I'd say it's because of that, not because we're counting, because the frequency is always going to be a count. It's going to be discrete. Okay, but determine whether we should use a histogram or a bar chart. A histogram is the appropriate representation because the data is grouped and quantitative. Yeah, but I think also because it's continuous data here. Continuous data, rather, sorry, it's discrete data. Oh, that's interesting. I don't know. Actually, I think that you could actually have you could have bars which say, you know, from 0, 0, 1, 2, and 3. I mean, you could potentially make a bar chart here, I think. You could have 0 to 3. I mean, you could have this on your chart. You could have a bar here which is saying 0 to 3 chicks hatching. You could have another bar which is 4 to whatever the next one is, okay? You could have that, but I think that because it's quantitative, on this axis here. And because we can group the data, then we can make a histogram. And I think that's what they're saying there. Okay. I mean, it's really kind of interesting how they've made those groups. They've made those groups by saying 0.5 to 3.5. In fact, they're not including 0 there. Is basically catching 1, 2, and 3. Yeah, and when and then the next one, 3.5 to 6.5, catches 4, 5, and 6. And that's an interesting way of doing it. Okay, you can see how they've turned that into a histogram. Perhaps that was a valid and interesting point there. Okay, so that's how they've changed discrete data into groups in this case. Okay, right. Now they also talk about just having more discrete data here, where they're saying your original information isn't in groups, and they're saying you can change your histogram, if you like, into a line chart here, a vertical line graph. And they're saying this is also another valid way of representing your data, of representing frequency histograms. You can make vertical line graphs. So if you've just got numbers at the bottom, there's 0, 1, 2, 3, 4, and 5, then you can just come up with your height of those things. So that would be valid. So yeah, it's very interesting, this point here where they've said, if you've got between 0.5 and 3.5 chicks hatching, that's just really our grouping that we've got for in order to make a histogram, in order to come up with an x-axis scale and to plot these things on there. Okay, and you can see when you're doing that, essentially, for example, from 4, 5, and 6 is between 3.5 and 6.5, or 4, 5, and 6 would be in the middle of that category. And if you're going to do the same in this case, well, you'd have 0 in the middle of minus 0.5 and 0.5, which kind of doesn't make any sense, which is why they're flicking to the vertical line graph. Okay. Yeah. Yeah, and okay, so I mean, that's another reasoning here that why they're saying, well, in fact, we're going from a line to a bar, going from 0.5 to 3.5. I've talked about that enough. Okay, 5C is there. Okay, so you can have a go at those questions. Certainly have a go at that last one because it's dealing with that issue of 3.5 to 4.5 in order to make this frequency table. And next time round, we're going to be talking about outliers. We're going to be talking about skewed distributions, so a load more definitions as well. And there we go. I'm going to stop there. Thanks for listening, and good luck with the exercise. Hopefully see you back next time.